Okay, so how to write the Spice code? So in general, Spice code, I'm saying we can afterwards simulate it on any simulator. Okay? I will use NGspice today. I will show you. So how to write the Spice code? That is one question. In Spice code, I told you already. Basically, we write the information of nets, how these components are connected, in which way they are connected, what are the values, and whatever we write. Suppose we want to take output from here, we will write it. In general, in any tool, this is the thing what they follow. Even if you are dragging and dropping the code, or even if you are writing some Verilog or something, but in background this is what happens. Okay, so I have like simplify it in few 7 steps. For now, just listen it, and then when we will do it, we will understand it better. So we open any text editor, and we will save this text editor with .sp extension or .cir extension, anyone which you like. So I like .sp, so I will save it .sp. So suppose I have designed an inverter, so I will use inv.sp. Okay, so this must have some line. I'm giving a line number like that. So first line, never write anything on the first line, because that first line is by default commented. So whatever you write in the first line, simulator will treat it as a comment line. Afterwards, see, there is no specific order. You can write in any order, but to make life simple, I have made this order. In second step, what we do, we include the model file. Okay, but if you take this example, here model file is not required. Model file is required when you are using MOS, diode, or these kind of things you are using. No? You are using something from the process design kit. Okay, so if it is not there, leave it. Third is component information. Now from here, your code starts. Okay, so I want to write the code. Say, so there is one component, I'm calling it R1. There is another component, I'm calling it C1. Okay, R1, C1. Okay, so how will I write? Suppose I will write R1. So I have given number 1 and 2 to these nodes. You can give anything, A or B, or anything 3 or 4. Doesn't matter. So I have given 0, 1, 2. So there are 3 nodes only. Okay. So R1 is connected between 1 and 0. Okay. And the value, say 100. So 100. So this is done. Next, C1, C1, C1. Connected between 2 and 0. Between 2 and 0. And the value, suppose I'm giving 60 micro. So 60 U. For micro, we use U. Okay. So there were 2 components we have already written. So third is over. Fourth, info regarding the connected source. Okay, so there is one input source connected. Okay, so I will write in a similar way: V in connected between 1 and 0, 1 and 0, and what is the value of this? Okay, so depending on the nature of input source, we can define it. Okay, so suppose for now, time being, there is a DC source connected, and the value is 5 volt. So you can write it like this. The third is over. Fourth, analysis to be performed, control statement. So if we are making some design, so we want to perform some analysis, like we want to do DC analysis or transient analysis, or let's say for AC analysis. So we need to mention that analysis. Okay, so suppose dot trans, and it has a syntax. So you not need to worry about the syntax. You not need to remember all the syntax. I will give you a quick reference sheet through which you can directly search and you can write it. So this is one quick reference sheet of Spice. So in this, you can see if you want to use basic component, what is the syntax for that? If you want to use sources, what is the syntax for that? Dependent sources and all these devices, what is the syntax? So it's already available there. And for various analysis you can do. So its syntax is already available here. So I will share this sheet with you. Suppose you want to use the pulse. So how will you use it? You just simply type pulse, search pulse in this, and you will find the pulse. So suppose this is one example of pulse. So suppose my B input is pulse. So how will I write? I will give the name pulse, and then lower value V0, the starting value, say 0 volt, then V1, upper value, say 5 volt, and TD is a delay time, then TR, rise fall time, and TO is the total time period. So that's how you can define it. So you just take this quick sheet and you just open it, search for the pulse, write the syntax, and go ahead with the simulation. Your simulation should not affect you. Like you should not memorize a lot of things to go with. Okay. So what I said, fifth is which operation I want to perform. So I have written, suppose I want to perform a transient analysis. What is transient analysis? Any analysis you are doing with respect to time. Okay. For example, this is the pulse. So this is with respect to time. This voltage is with respect to time. So if I want to design an inverter and I'm giving input this, so I will do transient analysis to see the output of the inverter. It might be opposite to this. Okay. And along with this, I need to use control statements because those are the spice syntax. Okay. So you don't worry about that. You need to write after your analysis like control. I will share a sample code with you and then run. You want to run it. So you need to write run after that. Okay. And when this is done, what you want, you also want to see the output. And suppose you want to see the output at this point. So what you will do, you will write the plot. You want to plot that. Okay. Suppose you're giving this input and you want to see the output. This is inverter and you want to see the output. So at output, you will write plot. Whatever node is there, for here example, node 2 is there, you will write 2. Okay. How will you write? Plot V of 2. You are, suppose you're plotting voltage at node number 2. Okay. So after that, everything is done. The output waveform we have done. And then last thing is end the code. So how will we end the code? To end the code, we have only two things. We will write end C and dot end. That's how we will end the code. Okay. So don't worry if you didn't understand it till now. We will do a code live. Then we will understand. I will share the code and everything. Okay. So my aim was just to give you a basic idea through this slide. Okay, so another example. So to understand this, what is the difference from the previous one? Here we have a device. Suppose I want to use the mouse. Earlier, I have given this example. So where I was using a resistor, so I have written the code something like this. Okay. Now, if I want to write for this, so earlier I was not using the second point model file. Okay, but here since I'm using MOS, I need to add the specific model. Suppose you are using TSMC 180 nanometer technology in this. So you need to include that model file into this. Okay. So for that, we will write model here. So you can do one thing, like if it is somewhere in your computer, you can give the path. That is one way. Another way, sometimes people, if don't understand, they copy paste all the model file at the below of the code. But that is not recommended. It is good to just include the model file. But for time being, suppose you don't have any model file, so Spice take model by default. If you write something like this dot model, so I am telling the second line dot model. So this is one NMOS. This is one NMOS. The dot model. I'm giving name N1 NMOS. Okay, and there are level. You might have heard 49 level, 30 level, 21 level. So these level are basically modification. You don't need to bother about all these things. And after that version. So you will write version, which version it is. Suppose 3.3.0. So that's how you include the model file. And if you are using PMOS, similarly you will do for PMOS. You will give, see this one, you can give any name. So I have given N1 for simplicity. For P1, you can give P1 and you will replace this with a PMOS and the same thing. So model file get included. Okay, so next is information of the circuit component. So here, if I have NMOS, so there is a way. So suppose this is at lower potential. I'm calling it, suppose this is on ground. Okay, so this will become source and this will become drain, isn't it? Because it's a like a symmetric device. So depending upon the input provided, the source and drain will comes out. So if I have given made it ground, so it will become source. It is drain. This is gate in any way, and this is body. So MOS is a four-terminal device, right? Generally, sometimes we miss the body, but when we are writing Spice code, we need to specify where the body is connected. Okay. So generally, what we do for NMOS, we connect the body to ground. And for PMOS, we connect the body to VDD. Okay. So to write code for this, how will we do that? I'll give you one example how to write a Spice code for MOS. It's very simple. So suppose I am giving name it as MN. Okay, you can give any name. I'm giving it MN. First, I'll write MN. The same similar way where I have written R1. No, so similarly MN, and MN is connected between, earlier it was R, and R was connected between 1 and 2 in earlier case, and the value was 100. So now this MOS is connected between, I'll tell you, suppose it's a complex circuit. Suppose there are 2, 3 MOS stacked together. So we need to assign these number to all, and we follow this convention. See, I have made a mark here this way. So we start from drain. Okay, so we will write the drain point 2. After drain, that gate will come. The gate is connected 1. Then the source will come. Source is connected 0. And after that, we'll go to body. And body, what I say, I have connected to source only, and that is connected to 0. So 0. Okay. And what is this? This is N1. I have defined it here, N1. Okay. So that's how we write the Spice code for MOS. Okay. First, we have included the model, and we have written the code for MN. And after that, if you some W and L is given, these are the parameters which we generally set according to us. So you can mention W and W value and L and L value. Okay. But for time being, for simplicity, now I am not taking any W by L. So it will take a default W by L, maybe 2. W by L ratio 2. So something like that. Spice will take automatically. Okay. So that's how we write. Like this was a new step which we included here, and this we included earlier, but the way of writing was different. Other steps are same. Okay, we will write the connected source, whichever source is connected. Suppose input is connected here, we will give the information. After that, we'll perform the control task. Okay, then to see the waveform, suppose I want to see the output waveform here, so I will write plot v2. Okay, and then end dot end c and end. Before actually jumping to the tool, we will write the complete code on pen and paper. This is first line. And first line I have given inverter. You can left it blank also. My first Spice code. Or you can write hello world and anything. It will not come anywhere. Okay. After that, add the model files. So I am calling it MNMP. How will I include model files? So the similar thing we will write on the text box model. After that N1. Okay. Then NMOS for I'm writing NMOS. After that level 49 and version. So this is when we are not including any file. We don't have any file. So we are writing like this. Okay. And after that for PMOS, I'm writing it for you model P1 PMOS same level 49 version 3.3.0. Okay. After that 1 2 is over. I want to write this first information of MN 2 1 and 0 and then N1. So the way of writing, first to mention the name. So this is MN. So we have written MN. Then the convention was to start with drain, then gate, then source, and then come to the body. So drain is at 2. So we have written 2. Okay. Then gate is at 1. We have written 1. Then source at 0 and the body is connected to 0. So written 0. And this is what N1. For MP, yeah, 2 is drain 1. Then 3 is the source and 3 P1. Okay. PMOS. In PMOS, what happens? In PMOS, what happens? The source is connected to VDD. Source is at higher potential. So how we see it? It's PMOS. It should have the more positives. Positives more are at VDD. So this becomes source for this. Okay, and the remaining will become drain. The gate is same always, or body. You can. So the next we have done this. We have defined the devices. There were only 2 components, NMOS and PMOS. So we have written it drain, source, gate, body. Okay. So now next step is to information of the connected source. So this is interesting. So one source is connected VDD, connected between 3 and 0, 3 and 0. And the value of VDD Also we need to provide similar, like we have written a resistor connected between 1 and 2 and the value is 100. Similarly, we will give the value. So the value I'm giving 5 volt, say. Okay. So next, another source is connected V in. In V in, what we want to give it pulse because we want to see the inverter's output. So that is why specifically I have shown you the pulse. Okay. So pulse is little something like this. Okay. So the name is, so I'm writing this because this is, it has many steps. I have already shown you all this, like rise time, fall time, like first value. So it is V in, the name is V in, okay, and connected between 1 and 0. So I'm writing 1 and 0, PULSC. So we will write like this. After that, initial value is 0, 0. After that, highest value is 5, and then rise time. So rise time gives say 10 nanoseconds. So initially delay I have considered 10. Okay, and rise time I'll write it little lower. Otherwise it will mix up. I'm repeating it. V in, connected between 1 and 0. Type is pulse. Initial value 0, 5 volt. Delay is 10 nanosecond, and then rise time is say 1.1 nanosecond, and the fall time is also say 0.1 nanosecond. Okay, and then that width, that on time is so we'll give it a little higher, say 30 nanosecond, and the complete time period I will give say 60. These can be different also. So this is the complete syntax for pulse writing. So I will remove this line to avoid any confusion. Okay, so we are done. V in and VDD and V in, there were two sources. So we have done the fourth step also. But with in fourth step, after that we will do the analysis. Okay, so analysis, what kind of analysis should I do? Because at input I'm giving a pulse and I want to see the output, inverted pulse. So what analysis should I do? Transient analysis, because it is with respect to time only. No, we have written everything in terms of time. So next is analysis. So analysis, we are doing transient analysis. Okay, so the syntax for that is trans, TRAN, tran. Okay, and after that, start and stop time. We consider this start and stop time. Dot tran, then start and stop time. So start time I'm giving 1 nanosecond, and stop time I'm giving say 17 nanosecond, more than that pulse. So transient I have given a start time 1 nanosecond, stop time 17 nanosecond. Okay, and after that I need to mention the control statements also. So what I'll write dot control. So it will be there in all the programs by default, and then you want to run it, so write run. Okay, so this step is over. After that, we want to plot it to see the waveform. Okay, so what I want to do, I want to see the plot of first waveform also and the second waveform also. Okay, and here in transient, I have given 70 nanosecond. You can give it, if you want to see the longer wave, you can give it, say, 200 nano. You will see the repeated pulse. Okay, so you can give anything. So I'm just erasing it to avoid any confusion. Okay, so next is to plot. For plot, I'll write plot. I want to plot potential at 1, V1, and then potential at 2, V2. And then I will end the thing. So two statement will come, and C and dot end. So this is the complete program. Okay. Now I would like to show you this thing on the simulator. Okay. Okay. So this is the NGspice. I have already installed. I'll how to invoke it. I'll tell you. So this is my folder, and I have already written this code. If you want to see inverter, so this is the code I have written. Okay. So in the first, I have written MOS inverter, and then I include the model, then the information of the components, then afterwards the sources and the analysis and controls, and then plot, and then end. Okay, so I'll run it, and how to run it? Just simply write NGspice. After that, give the file name. The file name is inv.sp. Okay, so now enter. So can you see this V1 is my input? It is in red. Okay, and this V2 is my output. This is in blue. So obviously some some delay will come, inverter delay, and this overshoots will come. You can see. Yeah, we got the inverter output. Wherever we have high, we got the low with these errors. No, so this is okay.